Okay, let's start. Hope you enjoy yesterday evening. The dancing, the karaoke, and all of that. So let's finish this series of lectures. I will try to summarize, first of all, where we are standing, where we left yesterday, and then I'll try to convince you that all the efforts we have been making so far will pay us back with some connection to observations. Okay, so I will start by reminding you that yesterday we defined this quantity zeta, which is defined to be the gravitational potential that we define to be the diagonal part of the metric, of the spatial part, plus h delta phi, let's use the delta rho over rho dot, where delta rho is the fluctuation of the energy density, rho dot is the derivative of the background. And we show that during inflation, at least if we are dealing with one degree of freedom, which is the inflaton field, this guy in fact coincides with this quantity here. And therefore, having spent some time in determining what is the power spectrum of a massless scalar field, we learned that in fact this quantity P zeta has a power spectrum which I can compute in the flat gauge. I remind you that the flat gauge was defined to be yesterday by the gauge for which psi is identically 0. And therefore we can say that the power spectrum is in fact equal to h over 2 pi square, which is coming from the delta phi. Then we have an extra h square factor from here divided by the time derivative of the value of the scalar field of the background square at the denominator. Okay. We also learn that once we have this expression, we can compute the spectral index, which is defined to be the derivative of the log of the power spectrum with respect to the log k. And we learn that, in fact, this object can be expressed in terms of these roll parameters. Let me write them here again. Epsilon is defined to be 4 pi g Newton times phi dot 0 square divided by h square. And eta is defined to be 1/3 times the second derivative of the potential, whatever it is, divided by h square. So we learned that once we define these two roll parameters, the spectral index is defined to be the deviation of the spectral index from unity is 2 eta minus 6 epsilon. And we left yesterday saying that this is a fundamental result because, of course, it tells you that the spectral index is not exactly unity, and it deviates from unity only by a small amount. Okay, so that was the recap of what we left with yesterday. Now, the quantity zeta is important for two reasons. The first reason is, of course, as we said yesterday, by construction, it's gauge invariant. The second reason is the fact that in a single field model of inflation, which in fact are the ones that we talk about so far. So far I introduced only one single scalar field, the inflaton field. The important information is that within this assumption, zeta is constant on super Hubble scales. What does it mean? It means that zeta dot is equal to 0 if I take a mode, let's say k, such that k divided by AH is smaller than unity. So when I look at perturbations, when I do the Fourier transform of this object, and I'm looking at perturbations with a wavelength which is larger than the Hubble radius, this object is constant. Doesn't change with time. Okay? So I will show this property in a minute, but before doing that, I want to tell you why it is important, why it is a crucial step in all this business. And let me explain it by a simple picture, which is the one that we saw already many times, but now it becomes a little bit more clear, I hope. So we have log of A here, let's say. Here we plot any quantity we like. We have the Hubble radius during inflation, and then inflation ends, and the Hubble radius starts growing. And in fact, it coincides, apart from a numerical factor, with the horizon. Now, let's consider a perturbation, a given wave number of the zeta quantity. So the zeta is born, like any other fluctuation, on sub-Hubble scales, so it is born here. I'm plotting the wavelength of this mode, so let's say that I want to characterize the zeta sub k. This wavelength is growing, like, so this is the lambda, and it grows, of course, like the scale factor. In the plot, of course, it's just a straight line. And then it leaves the Hubble radius at some point during inflation. It freezes out because we want to, in fact, we will spend some time in showing that zeta is constant. And then much later, it re-enters the horizon. Okay? So this perturbation spends, inflation is taking place at a fraction of time which is 10 to minus x seconds, where x is of order of 10, 20, 30, depends on the model. But what is interesting is the fact that this perturbation is living outside the Hubble radius for a long, long time. And we are talking about billions of years. And then it re-enters the horizon. There are modes, for instance, that are re-entering the horizon now, for instance. And then they become, they are subject to the local dynamics, and they leave their imprint on other observables, for instance, the temperature or the delta rho of the matter, of cold dark matter, for instance. So what is the idea? Here, zeta is during inflation, zeta is the one that we wrote before in the flat gauge, is equal to h delta rho over rho dot of the inflaton field. But then, of course, when inflation ends, the radiation is taking over. Inflation is torn off. A plasma of relativistic particles is formed, and of course this fluctuation goes into the fluctuation of the plasma of radiation. And since there is an imprint of this fluctuation that comes from inflation, this fluctuation looks like a fluctuation of the temperature of the photons of the relativistic particles that you created after inflation. Okay, then after a lot of time, the matter-dominated period starts, and of course this fluctuation also gets communicated by gravity to the fluctuation of the cold dark matter, or the baryons, whatever. This fluctuation can eventually grow because of the action of gravity. Gravity is attractive, so it likes to clamp matter, and of course this fluctuation will grow and will give rise to the structures we see today. Okay? So the idea of behind the inflationary cosmology is the fact that the fluctuations that we see today as classical fluctuations of the temperature of the CMB, of the distribution of matter, are in fact of quantum nature. So if you like, this is one of the best examples of quantum mechanics in action. Something is happening at the microscopic level. We solved the equation of motion of a quantum field. We computed its power spectrum and so on. Then these fluctuations have a wavelength that gets stretched to macroscopic scale, cosmological scales. And today we see them in the form of classical fluctuation, which we call temperature anisotropies or galaxies and so on and so forth. So you see? So the beauty of this picture, which in fact, as far as I'm concerned, is relying on this assumption here for the time being. Then we will extend this assumption, we will release it. But for the time being, let's focus on the fact that zeta is constant. The fact that zeta is constant when it is on super Hubble scales, it allows you to make a prediction for quantity that you measure today, coming from the theoretical prediction that you have at 10 to minus 30 seconds. Okay? And of course, this is possible because this zeta is constant. So anytime it leaves outside the Hubble radius does not change. So the imprint that you have here will be communicated later on. That is the key point to allow the fact that you can make a prediction and measure something many billions years after. Okay? Is that clear? That's a key point of all the computation. The next step will be to show that in fact this property is true. And let me sketch you the argument. In fact, you can do it again. It's one of those computations that you can do in a rigorous way, but I will do it with another trick in order to speed up the demonstration. So again, I'm working under the assumption that there is this energy density and this pressure in my system. In general, the rigorous way will be to take the covariant derivative of the energy momentum tensor, which has to be equal to 0. Okay? In T mu nu, you have the pressure density, you have the energy density. And then what you have to do, you have to perturb this equation. In other words, you linearize this equation, and you see what the linear part of the equation, how it looks like, because we are interested in delta rho, for instance, how delta rho behaves. Okay? So if you do that, you can do it. It's not a difficult computation, but I don't have time to do it now here, to do all the steps. I will perform a trick, which is the following. Suppose that I'm looking at my Hubble radius of the size is h to the minus 1. And I'm looking at a perturbation. I'm interested to look at the variation with time of my quantity zeta on super Hubble scales. So I'm looking at perturbations that are of this form. The wavelength is very large compared to the Hubble radius. Okay, so yesterday, if you remember, we started from a perturb metric, which was written in the following way. So we said that we have 1 plus 2 phi dt square plus 1 minus 2 psi a square dx square. And then if you remember, we found the rule of transformation for this psi, this gravitational potential, and out of which we constructed the gauge invariant quantity. Now, since I'm interested only in perturbations which are on super Hubble scales, first of all, let me exponentiate these two objects for simplicity, even though you have to think of them only linear. So I'm going to write down them in this way. Okay? And as I said, I'm interested in perturbations whose gradients are small compared to my observer, who is inside this Hubble radius. And therefore, what I can do a change of coordinate system, which is based on the fact that if I am a local observer and I have a background, a wavelength of a perturbation which is larger than the size that I'm probing, in this case the Hubble radius, this perturbation looks like a classical field. You cannot distinguish it for a classical field if the perturbation has a wavelength which is larger than my area where I'm computing background quantities. And therefore I can redefine this metric as in this way. I can call it dt square plus a bar square dx square, where now locally my new coordinates are such that dt bar, my new time, is equal to e to the 2 phi dt, e to the phi dt, and my scale factor, my local scale factor, is a bar, which is the initial scale factor times e to the minus psi. Okay? So I'm using the GR arguments, for which you can always find a system of coordinates where physics is local, and I redefine my coordinate system in such a way to eat up this perturbation, which again are on long wavelength mode. Okay? So now this is a universe which is unperturbed in these new coordinates, and therefore I can write down the equation of motion for the conservation of energy, and I will write it that in the following form. I have rho bar plus free h bar, which is my new Hubble rate, times rho plus p equal to 0. Okay? Because that is the equation that I have when my background is uniform, where now this dot is in fact, I have to be careful, this dot here now is d over dt bar. Okay? It's not the dt. Okay, so now, and also remember that h bar is equal to a bar dot divided by a bar, okay, where the dot is again the new time, the derivative with respect to the new time. Okay, so now I use this trick, and notice that in fact the dt bar is here, 1 over dt bar is here, 1 over dt bar is here, so I can eliminate the dt bar and I put the dt, because in any case I have the right hand side which is 0. And then I go back to my original coordinates. Okay, so from the h bar, you're going to get something like, which is h, the usual h, minus psi dot, by the definition of the a bar, you see. And then here, I have times e to the minus phi. But as I said, the e to the minus phi will go away when I also take the derivative with that. So if I now go back to my original coordinates, the equation of motion, and I perturb it, because now I want to consider all the perturbations, I will have an equation that looks like this. I have an equation which is delta rho dot plus, I only consider the part of the perturbation, plus free h delta rho plus delta p, okay? And then I have minus free psi dot times rho plus p. Okay, and let me put a 0 here, because I want to remind myself that I'm dealing with background quantity equal to 0. Okay? Now, you see, I can define my delta P. In general, the pressure density, the perturbation of it, has two components. One that I can write down as, so let me write down the definition. So it's C sub square delta P over delta rho plus delta P non-adiabatic. Let's write it in this way. No, okay, let's use, okay. So the pressure density has two components. One that comes from the dependence of the pressure over the energy density. So if I have a pressure that is a function of P of rho, okay, the total energy density, then there is a non-adiabatic piece. So in fact, let's put an N here because it's non-adiabatic, which counts for the fact that in fact, in general, it's not true that the P is a function of rho. In the cases that we are dealing with, the case of the single degree of freedom, which this is true. But in general, when you have two fluids, for instance, suppose that you have two fluids with pressure P1 and P2, and pressure densities, and you have rho 1 and rho 2 for the two energy densities. In general, it is not true that you can write down the P, the total P, as a function of the total rho. Okay? The simplest case, think of the radiation plus matter. They have a different equation of state. There is no way you can write a relation like this. So you always have to introduce a non-adiabatic piece when you have two fluids, for instance. But now I'm using the trick. Now I want to write down this equation I want to reduce myself to the zeta. But you see, since the zeta is a gauge invariant quantity, this time I computed it not in the flat gauge, I computed in the uniform energy density gauge. So I work in a gauge where delta rho is equal to 0. Okay? If I do that, then of course what happens is this zeta becomes equal to psi, because I'm working the gauge where delta rho is equal to 0, and therefore the equation for I have psi dot equal to something, but that psi dot is equal to zeta dot. So I have zeta dot equal to, I get it from here. From here I get since delta rho is equal to 0, okay, so I have, sorry, here I wrote something completely wrong. Sorry about that. This is delta rho, and C sub S square is delta P over delta rho. Okay? So in the gauge in which delta rho is equal to 0, this is 0. I am only left with a delta P non-adiabatic, and then I have to divide it by this guy here. So what I get a delta P non-adiabatic is the right-hand side divided by times H divided by rho 0 plus P0. Okay? This is the equation of motion of zeta when it is on super Hubble scales. This is a generic equation. In the case in which I have only one fluid, I have only one degree of freedom, which is the scalar field, then for 1 degree of freedom, what I get, since in this case I can express the pressure density as a function of the energy density, I get that zeta dot is equal to 0. Okay? So that is the crucial argument that makes the computation possible. In the sense that I want to connect to observations. Of course, we can release this assumption, and in fact I would like to give you an example where we keep also the right-hand side, which is not vanishing. But for the time being, we will restrict ourselves to this case. Questions? Yes. Say it again. Why did I do it? For convenience. Because this equation is generic. Then I choose a gauge. Because I want to speed up the computation. You can choose any gauge, but you can also work in the other gauge where psi is equal to 0. But here, in order to show that zeta is constant on super Hubble scales, I'm using the shortcut of using delta rho equals 0 gauge, and therefore this piece goes away. This piece goes away, then the adiabatic part of the pressure goes away, and then I'm left only with that. Okay? Of course, if you work in another gauge, you're going to find the same result, because also this delta P non-adiabatic, you can make it gauge invariant. Okay, other questions? No? All right, so now let me make the first connection to the observations and try to understand how big is this fluctuation in the temperature when the temperature is born, basically at the last scattering surface. So if you remember that the first lecture we said that photons, well, the universe becomes transparent to photons when the temperature of the universe is a fraction of EV, and we call it last scattering surface. And if you remember, we computed the size of the horizon at that time, and we concluded there is an horizon problem because at that time the horizon was pretty small, and if we take our universe and we crash it back to the time of the last scattering, that region was containing 10 to the 6 Hubble volumes at the last scattering surface. Okay, so what we want to do now, we want to take this picture again. So we are here at the center and we are getting photons. So we said that, okay, so here is a sketch of the Hubble radius at the last scattering surface. So each of the spheres have a size which is the Hubble rate to the -1, the last scattering surface. And we are here, we are receiving photons on this from all over the places, as we said. And in particular, these photons, when they were emitted, had a given temperature. And but also there are anisotropies now, because of course this inflation is perturbing the things around, and you have perturbations that we want to now to evaluate at the last scattering surface. So in particular, I want to analyze for simplicity perturbations that are larger than the Hubble radius at the last scattering surface. Okay, so I want to look at objects which are a perturbation whose wavelength is larger than Hubble radius at that time. Okay, so as I said, the idea is the following: the scalar field is driving inflation. There are perturbations around. You can put the perturbation in the psi, you can put them in the scalar field, you can do whatever you like, but at the end of the day, these perturbations are left imprinted in the radiation that you create after inflation. And therefore, you expect that not only the photons will have a common temperature on average, but of course they will also bring some anisotropies with them. And we want to, because of inflation, and we want to characterize them. But in order to characterize them, I'm just working on the assumption that I'm looking at the wavelengths which are large enough, because I want to make the computation easier. And of course, you know very well that you have seen this picture of the temperature anisotropies that the map has been produced by WMAP and then by Planck. So you have seen for sure this picture of the, let's say, L square C sub L, where you have these famous peaks as a function of L, which is the multiple, which is pi over theta. So basically what people do, they take photons coming from some two regions, let's say. These regions are separated by an angle theta, and then they do the Fourier transform. They compute the two-point correlators of the temperature of these objects, and they subtract, of course, the average, and then you have this famous peaky behavior. So basically, this is a two-point correlator of the fluctuations of the temperature as a function of angle, if you like, or the inverse of the angle. And what I would like to do now is to concentrate on this part here. Okay, the part that has a small l and therefore large angles, meaning that in this picture I'm looking at photons, okay, that are separated by an angle which is larger than the Hubble radius at the last scattering surface. Okay, And in fact, it turns out that experimentally, this object, this behavior is quite flat, in proper units, of course. And it turns out that, as you know, delta t over t is of order of 10 to minus 5. So we measure anisotropies, which are small. In that sense, we can do linear perturbation theory when we deal with them. And therefore, we expect that we don't need to go to higher orders. Okay, so what I would like to do now is to show how to connect this quantity, which is basically the size of the plateau, to the prediction of inflation. Okay, because when I do that, I will be able to explain why there is a plateau, first of all, and this is related to the fact that the spectral index is close to 1. And also, I will be able to fix the amount of perturbation during inflation to the observation. Okay, so let's do this exercise. First of all, we need to relate delta t to the zeta. And once we are able to do it, we are basically done. That requires a few steps, which are elementary, but we have to take them. So first of all, suppose that I receive the temperature, I receive photons at a point which is central, and I call it TO because O stands for observer. So I'm the observer, I'm receiving these photons, and I collect them and I measure the corresponding anisotropies. So what is this temperature that I receive from these photons? It will be the temperature which was emitted at the last scattering surface. So here, this is the emission point. And of course, these photons propagate freely, but the frequency is reshifted. Correct? So here, I have to multiply by omega O divided by omega at emission, where omega is the frequency of these photons, because of course when the universe is expanding, the frequency of the photons, since it is related to the wavelength, it also changes with time. Okay? But now I don't want this quantity, I want the perturbation of this quantity. And to do the perturbation, I use the same trick as before. I say I'm only interested in perturbations that at the last scattering surface have a wavelength which is larger than the Hubble radius. And therefore, if I transport myself back in time and at the last scattering surface, I can redefine, if you remember, my dt bar, I can redefine local time as dt times e to the phi, where phi is the gravitation, is the lapse function. Okay? On the other side, what is the frequency? The frequency is the inverse of dt. Okay? Is the inverse of time. So here what I can do, I can see this, so I know that when I look at the photons, they have a given frequency, but locally this frequency is perturbed by the fact that I'm not living in a perfectly uniform universe. And therefore, this omega e, for instance, it will go like 1 over dt bar e, and therefore it will go like 1 over e to the phi. Okay? So from here, if I compute the perturbation of this quantity, what I will have? I will have the delta t observed divided by t observed, which is supposed to be the average, will go like what? Will go like delta t e over te, which is the intrinsic perturbation that this object has, because of course the temperature is by itself perturbed, plus, if I do it at first order, plus phi at the emitting point. Of course, I also have the phi at the observed point, but as you know, this is unphysical. I only measure in GR differences of gravitational potential, and therefore I can put it to 0 by convenience. So this is the expression that I want. So I measured a temperature anisotropy of the photon coming today, which is the sum of two pieces. The temperature anisotropy, this guy, the temperature had at emission, time, plus the fact that there is a frequency shift in my perturbed universe. Okay? Very well. So now, this phi, we leave it for the moment. Now we want to characterize what is this object here. And you will see it's not difficult, because I do the following. What is the energy density of the radiation? It goes like T to the 4. Okay? So I know that delta T over T is 1 over 4 delta rho gamma over rho gamma. And then I go back to my quantity zeta. Zeta, I computed in the flat gauge, for instance, and I know that it's h delta rho over rho dot. This is just the, so let's put also psi equals 0 here, because I want to use this flat gauge. This is the object. So how does it look like? So we also proved that this zeta goes through the history of the universe constant. It's always constant on super Hubble scales. So what is zeta during the radiation phase? Okay, so in fact, let me put radiation. During the radiation phase, it is equal to h delta rho radiation divided by rho dot radiation. But this is equal to h delta rho radiation divided by minus 4h rho radiation. Right? Remember that rho dot radiation plus 4h rho radiation is equal to 0, because here you should have the p plus rho, but p is 1/3. You sum it up, you cancel the 3, and you get the 4. Okay? So this is the relation. On the other side, the zeta is constant, and therefore this is also true, so that this zeta is equal to zeta radiation. So let me rewrite the expression. So the h goes away, so it's minus 1/4 delta rho radiation divided by rho radiation. This guy is also equal to zeta matter, where zeta matter is, I call it zeta sub m, is the value of zeta when the universe becomes matter dominated. And what is this? Is h delta rho matter divided by rho dot matter, and therefore is equal to minus 1/3, because the pressure for matter is 0, delta rho matter divided by rho dot matter. By rho matter. Okay? So from here I get the fundamental relation, which is 1/4 delta rho radiation divided by rho radiation has to be equal to 1/3 delta rho matter divided by rho matter. Okay? So every time there is a change from radiation to, well, when we go from inflation to radiation to matter, these fluctuations are communicated to the fluid using this condition, which is called the Adiabatic condition. Okay, so you get this. But you see now that 1/4 delta rho radiation over rho radiation is nothing else than delta T over T. I use the symbol here gamma because I want to remind you that we are dealing with photons, with relativistic particles, so I put a photon here. Okay? So we get this information that delta T over T so let's see if I can get, we get delta T over T, and in fact let me put the back label E, okay, is equal to 1/4 delta rho radiation divided by rho radiation, which is also equal to 1/3 delta rho matter divided by rho matter. Okay? And now we remember that the last scattering surface this last scattering is approximately taking place when the universe is matter dominated, and therefore I can use this expression. Okay, so now we say that delta T O divided by T O is equal to delta T E divided by T E plus phi, if you remember, at emission. Now the last step is to, where there are two steps more, to express this term here in terms of phi, and then phi in terms of zeta. And then we are done. As you will see, it's not difficult. I mean, this is just the algebra is very simple, but you have to stay with me. So here, I want to relate first delta rho matter over rho matter to the phi. How do I do that? In principle, what I should do is to look at Einstein equations. Einstein equations, as you know, have the left-hand side, which is the space-time geometry. The right-hand side, you have the matter. So I perturb the Einstein equation. I take the 0, component, and the 0, component on the left-hand side is the phi, and on the right-hand side is delta rho matter. If you don't want to do the expansion of the Einstein equations in linear perturbation theory and so on, you again use the same trick I told you before. You just write down, in the new coordinate system, you write down the equation. So again, I do the trick. I'm interested in perturbations which are larger than the Hubble radius. Okay? And what you can do, you can redefine your coordinates, and you write down the usual equation, h bar square equal to 8 pi g Newton divided by 3 rho, where now the h bar is the Hubble rate measured by a local observer, which is living in the presence of these new perturbations. The perturbation is constant on super Hubble scale, so the psi dot you drop it, and then you use only the phi. The phi this time does not cancel, because you see you have a 1 over dt bar here, but you don't have it there. And if you perturb again back to the original coordinates, what you find that delta rho matter divided by rho matter is equal to minus 2 phi. Okay, where the minus 2, so the delta rho comes from here, you see, and the 2 of the phi comes from the fact that you have 1 over dt bar square, because you have the square of the h bar, which brings a factor of 2, because you remember it's e to the phi, and then you have e to the 2 phi, you expand it, and then you get this thing here. The minus sign comes from the fact that the phi is at the denominator. So let me skip this computation, and you get this relation here. So from this relation, you can now get finally delta t over t, because delta t over t observed is going to be, as we said, is delta t over e, which is 1 over, so let's see where we are, is there. So we have the phi sub e, okay, plus 1/3 of delta rho matter divided by rho matter. But this guy, I know what it is phi sub e minus 2 divided by 3 phi at emission, and therefore it is equal to 1/3 phi at emission point. So, if you perturb your universe and you look at perturbations in the temperature on scales larger than the Hubble radius, you get that your perturb metric, your perturbed universe, is reflecting their perturbations in the temperature anisotropy by this formula here. This is the famous Sachs-Wolf effect. Okay? Okay, so we have this factor 1/3. All right, now the very last step is to go to the zeta, and you do it by the definition of the zeta, so the computation is also quite simple, and you do it in this way. So the zeta is equal to psi plus h delta rho over rho dot. Okay? Let me find the generic formula for you. So we know that rho dot is equal to minus 3 p, well, let's say rho plus b times h. Now let's say that the pressure is equal to W times rho, where W is a constant. It can be 0 for matter or 1/3 for radiation. So I know that rho dot is equal to minus 3h, 1 plus W times rho. Okay, so I plug this information into the definition of zeta. So I get zeta is equal to psi, and then I have minus 1/3 delta rho divided by 1 plus W rho. Okay, so there is a minus sign that comes from here. The 3 comes from there. And then I now use the information that I use two informations. The first one is that delta rho over rho, as we just said, is equal to minus 2 phi on super Hubble scales through the Einstein equations. So this is psi plus 2/3 phi divided by 1 plus W. Okay? And then the last information is that I can work in a gauge where, which is the longitudinal gauge that I introduced yesterday, where, and here you have to believe me because this is just an information I give you. In this gauge, psi is equal to phi. Okay, sorry, I don't want to show it because it's not that difficult, but just believe it. Okay, so in the longitudinal gauge, the psi and the phi are the same. So from here, what I get that zeta, if I work in this gauge, is equal to 3, 1 plus W times phi, which I factorize out. And here what I have 3, so I have a factor of phi plus 3W. Okay? So in particular, during the period of matter, so when I compute I'm putting myself in matter dominated, I know that zeta is equal to, so I put W equals 0, so I get phi over 3 phi. Okay? And therefore, when I go back to this relation, well, let's write it down on the top of the blackboard, otherwise it's squeezed. So I get a delta T over T, which is equal to 1/3 of phi. Okay, from there I read that phi is equal to 3 over 5 zeta, so it is equal to 1/5 of zeta. And this is the fundamental relation that you can use, that relates the observed quantity to the quantity which is predicted by inflation. Okay? Here is the quantum part of the computation, if you like, the inflationary dynamics that creates perturbation in this gauge invariant quantity. This gauge invariant quantity goes through different epochs untouched on super Hubble scales. It remains constant under the assumption of having a single field case. And then these fluctuations, that you can think of them as fluctuation of the energy density or fluctuation of your geometry and so on, according to the gauge you're working with, gets imprinted in the temperature anisotropy. You measure this quantity, and then you know the information about this quantity there. So this is the connection between the physics today to the physics of the very, very early universe. All right? Questions about these passages? Nothing? So let's see, I can take a 5 minutes break, so you can stretch your legs and so on, and we will make an example to compute this object for a given model, which is an interesting computation, I would say. All right? So let's take a 5 and then we will reconvene soon. Let's restart. I hope everybody's back. So what I would like to do now is to provide you with an example of a computation of the power spectrum, and of course the goal is to match it to the observed quantity that now we know it's going to be 10 to minus 5, because we were able to relate the delta T over T. So we know that delta T over T on sufficiently large scales is equal to 1 over 5 the zeta, and therefore the power spectrum of this quantity, that is something that you can measure, is directly related to the power spectrum of the zeta. Okay, so a few steps. So what is the power spectrum of the zeta? I write it, so let me define, I also defined it yesterday, but let's call 8 pi g Newton, we call it 1 over m Planck square. Okay, this is the reduced Planck mass. So I can write down the power spectrum in a convenient form, equal to h2 pi square, 1 over 2 epsilon m Planck square. Okay. And because remember, the epsilon takes care of the fact that you have a phi dot square in the definition of the power spectrum, and if you redefine everything in terms of the epsilon, you get like this quantity here, where you define the reduced Planck mass in this way. Okay, so now what is the rule of the game? I have to compute my objects here, my quantities h and the Hubble rate, at a given time, because of course they change a little bit with time, and that will also tell me the spectral index of this object. So the idea is the following: we take the same model as the one that we worked out a few days ago. We take a V of phi, a scalar field, the simplest one that we can imagine. We take a potential which looks like m squared phi square, divide by 2. Okay, and we define, if you remember, the moment where inflation ends is defined by the quantity, by the relation epsilon equal to 1. At this moment, the kinetic energy becomes of the order of magnitude of the potential energy, and then we have this scalar field which is rolling down slowly towards the minimum of its potential, and at every time there is a value which this field will acquire, and this value will correspond in 1-to-1 to the value of epsilon, and so on and so forth. Okay. In particular, it is useful to parameterize the values of the quantities in terms of the number of e-folds that you have till the end of inflation. We define the total number of e-folds to be the number of e-folds from the beginning of inflation to the end of inflation. But now, in order to link with observations, it's more convenient to define, let me call it delta n, not to confuse with the n that we defined previously. This is the number of e-folds till the end of inflation. Okay? So for instance, if the end is here, this will correspond to delta n equals 0. Okay? So how is it defined, this quantity? If you remember the way we derive under the Zeta conditions the number of e-folds, this quantity is nothing else than 1 over m Planck square, the integral from phi end to some phi delta n, which is the value when there are delta n e-folds to go, in d phi of v divided by v prime. That was the definition. Well, it was h dt, then we changed variables and so on, if you remember. And then, if you do the integral, which is trivial for this kind of potential, you get that phi square delta n is equal to 4 times delta n times m Planck square. So you see it's bigger than m Planck, but it's directly related to how many E-folds there are till the end of inflation. Remember that in order to for this inflating region to encompass our observed universe, you need a delta n of order of 60. So that is the number that we are going to put at the end. Okay? Where, of course, I have neglected here the value of phi n, because that will correspond to delta n equals 0. So I didn't bother to write it down. Okay, so once we have this object, then we can compute everything, because we can compute the values of epsilon, we can compute all the objects. So for instance, the epsilon, let me call epsilon delta n to remind myself that it is value when there are delta n E-folds to go. So the epsilon in this, with this definition of m Planck and so on, it is equal to m Planck square divided by 2 times v prime over v, computed at delta n square. Okay, so if you plug the numbers in, it's trivial, I'm not going to do it. You get that this epsilon delta n is 1 over 2 delta n. Okay? If you compute now the eta delta n, which I remind you is 1/3 v second divided by h square when there are delta n E-folds to go, you discover that this number is in fact equal to epsilon delta n, and therefore is equal to 1 over 2 delta n. Okay? And this allows me, first of all, to compute the spectral index. Because the spectral index now is going to be this famous 2 eta minus 6 epsilon. So the spectral index and zeta minus 1, if you remember, is 2 eta, and now I computed when there are delta n E-folds to go, minus 6 epsilon when there are delta n E-folds to go. But eta is equal to epsilon, so this is minus 4 epsilon delta n. So you see the spectral index is not exactly a constant object. It changes according to the number of E-folds that are missing till the end of inflation, but it goes very slowly, because this number then becomes, I use this object here, it becomes minus 2 divided by delta n. Okay? And now we can put a number. Now we put this object is measured through the CMB. The CMB, I told you, we are looking at the very long wavelength part of the perturbations, and in fact the CMB anisotropy is probing only a very small part of inflation. Only delta n is of order of if you look at the scales that the CMB anisotropy is probing, they corresponds to about a shift in the number of E-folds, which is about 5. So, but the largest scale is the current horizon, so we can take the plateau is for that region, so we take delta n to be equal to 60. So when there are basically still phi 60, so it's the value that phi gets when there are 60 E-folds to go, and we put a number here. So this is minus 2 divided by 60. It's minus 1 divided by 30. Okay, so it's minus 0.03, and this gives you n zeta equal to 0.97, which is an astonishing result, because the measurements are about that number. Okay, so you see, inflation is able to tell you that the spectral index is not equal to 1, and for the computation that we have made, the delta n is about 60. You plug this number, you have no reason that it should work, but it does work. It does work in an amazing way. So this to me is a beautiful result. I hope for you too. Okay, so the next step I want to take is the following. I want to characterize the, if you remember, I promised you to explain why this mass has to be of order of 10 to the 13 GeV, or 10 to the 12, I can't remember now the exact value. Let's see how this thing goes. So I can erase this figure. And let's compute the power spectrum. So we said the power spectrum, P zeta, is I cancel it. Yes, it was 1 over 2 epsilon m Planck square times h over 2 pi square. And I want to compute it everything when there are delta n e-folds to go. So we said that epsilon delta n is 2 divided by delta n, right? No, sorry, 1 over 2 delta n. Now, what is h square? H square in this units is equal to 1/3 the potential divided by m Planck square. Remember that the Planck square is 1 over 8 pi g Newton. So this is 1/3 m square phi delta n square divided by 2. Okay, and then there is the m Planck square. And then phi delta n square was what? Was 4 delta n times m Planck square, right? So here, apart from the coefficients of order unity, which we don't care too much, what we get is that the power spectrum goes like what? Goes like epsilon, which is, so I put delta n at the numerator. Okay, I'm forgetting all the coefficients of order of 2 and so on. Then I have m Planck square. I have h square over m Planck square. Okay, so I get, first of all, I get the m square. I have a phi delta n, which is, let's say, delta n square from here. And then I have m Planck square. No, sorry, this is only delta n. Okay, and then I have m Planck square. Okay, and then I have another m Planck from here, so I put it a 4 here. Okay, so you see this object goes like in terms of the masses, goes like m squared divided by m Planck square. Okay, then there are coefficients of order unity. We don't care about that for the time being. Of course, when we want to compare to the exact, with the observation, we have to do much more careful. But for this computation is enough. We said that delta t over t is 10 to minus 5. So the power spectrum is the square of it, 10 to minus 10. So from here, we learn that m over m Planck has to be 10 to minus 5. And therefore, m Planck is 10 to the 18 GeV, so you get 10 to the 13 GeV. Okay? So this computation allows you to fix the mass of this scalar field to be quite heavy, much heavier than the electroweak scale, for instance, but it's fixed by matching with the perturbations. So it's basically a free parameter. This is nothing that you can do. It's just a mass term that comes out this way, and then of course you can construct, you can rely on your high energy physicist friend to tell you, he will tell you or she will tell you if 10 to the 13 GeV is a good example or not. But that's what it comes about. Okay? So once you have your preferred model, you go through this computation and you find the typical mass scale of your potential. You find the n zeta minus 1. And luckily nowadays, if this number in your preferred model turns out to be too far from this central value, which is about this number here, then your model won't work. You just throw it away. All right? Okay. So now let's take a few, let's make the last effort, I believe, but as you will see, doesn't, this effort, based on what we learn, it won't cost you so much. And is to look at the other perturbations that inflation is able to produce, and those are the tensor modes. So far we only look at the scalar perturbations, but of course inflation is making another prediction, which is the fact that you also have gravitational waves around produced during this period, or better to say tensor modes. And let's compute their power spectrum. Okay? So what I want to do now, I want to talk about tensor modes, because those are another fundamental prediction of inflation. To do that, what I do, I go back to my counting of the degrees of freedom, and I remind myself that in fact there are transverse free and traceless objects. There are two of them, 2 degrees of freedom in my metric. So I'm going to use this perturb metric now. I don't care anymore about scalar perturbations. I only care about the tensor modes. So what I do, I write down, I perturb my metric in the following way. And I introduce these degrees of freedom that are traceless and transverse free. Okay? All right. So now, once I have written this metric, what I have to do is to plug this metric into the Einstein action, expand it in powers of these tensor modes, this h, I, j, and then I have to look how it looks like. So I'm only dealing with the quadratic part of the action. So that's okay. So if you look at the way it's written, the final result, I write it, is 32 pi g Newton times the integral in d4x of the square root of minus g. And then here you have basically h dot ij squared divided by 2 minus the gradient of the hij squared divided by 2. Okay? All right, so you see here I have this factor, which is, I can rewrite as m Planck squared divided by 4, using my definition of m Planck. So you see, of course, I have to canonically normalize the field. I can introduce some other field, Vij, which is now canonically normalized, which is defined to, I say that Hij is equal to 2 times Vij times divided by m Planck. Okay, so now this Hij has dimension 1. And then, of course, I do the usual trick of writing down the equation of motion and so on. But you see now, I don't have to make any computation. You see? Why? Because I solved already for you the case of a massless scalar field. This action is the action of a massless scalar field, with the only complication then, of course, there are degrees of freedom hidden in this tensorial structure. But if I want to compute the power spectrum, I already know what the power spectrum is of this object, of this total degrees of freedom. The pH, if I count all the degrees of freedom, I have 2 degrees of freedom because I have the famous cross and plus degrees of freedom. You remember yesterday we also counted how many degrees of freedom you have when you look at the spatial part of the metric and then you reduce by imposing the traceless condition and transverse free. In 3 dimensions, so in 3 plus 1 dimension, you have only 2 degrees of freedom. Then you remember that you have this factor of 2 that comes from the normalization of the action. And what is the power spectrum of this guy? Okay, so we learn has to be 8. The counting. Now you tell me what is the rest. Some of you. So it's a simple massless scalar field. So what I have to put here? H over 2 pi square. Okay? So you see? Rather trivial. And what if I define this power spectrum to go like, which is what people do, like k to the power nt. For some reason, there is no -1. If I ask you what is nt, you tell me? No, that's the definition, but the final result, what is going to be? No, 0. Okay, 1, 0, no. But closer to 0. What is the spectral index of a massless scalar field that lives not in de Sitter but in quasi de Sitter? Because inflation does not have epsilon equal to 0. We prove it. It's -2 epsilon. Okay? So this is the final power spectrum of the tensor modes. So you see, we don't have to do any computation based on what we learned so far. And we also know the spectral index. And then, if inflation is taking place through a single field model of inflation, so a single degrees of freedom, then you can write down now a consistency relation that in fact people try to find ways to test, which is the following. If I divide pH by p zeta, sorry, of course, I forgot here something, which is the M Planck. Okay, so if you write down this ratio is what? If you remember, p zeta goes like 1 over 2 epsilon M Planck square h over 2 pi square. So if you take now this ratio between the two, if single field model of inflation is correct, so if this result is correct, then the ratio between the amount of tensor modes and the amount of scalar modes that you have should be equal to 16 epsilon. And this epsilon is in fact nt, related to nt. So this guy should be -8 nt. Okay, so there is a fundamental relation that relates quantities that you can observe if single field model of inflation is correct. You should, p zeta we know, it's about 10 to -5. We measure for the CMB anisotropy. pH we have not measured yet. And of course, then NT, we have not measured it, because of course we don't know we haven't measured the power spectrum. But if one day we will be able to measure the power spectrum and its tilt, the n sub t, then there is a fundamental relation. In fact, this quantity is called usually small r, that relates observable quantities. And of course, if this relation will be confirmed, this will be, of course, telling you that most probably inflation goes through a single degree of freedom. Okay? So there is a lot of effort now to measure the power spectrum from inflation coming from the power spectrum of the tensor modes coming from inflation. The way you do it is simply looking at the polarization of the CMB anisotropy, because at the last scattering surface, if there are tensor modes generated during inflation, these tensor modes, when they go through a given region, a last scattering surface, they perturb the underlying space-time, and they induce, when the photon scatters off the electrons, they induce a given polarization that people now are looking for. It's called the famous B mode. And there is a lot of effort to try to measure this thing. If it is measured, and within some accuracy, then we will have an handle on this amount of tensor modes. I would like to conclude the lectures telling you two more information. First one is the following. As you see here, differently from this expression here, you see this expression contains, apart from m Planck, contains two basic quantities. H, the Hubble rate, and I remind you that H in this unit is 1/3 V divided by m Planck square. But then it contains also an epsilon. Okay? The pH does not depend on epsilon at all, it only depends on the Hubble rate. So why the tensor modes are so important is because a measurement of the power spectrum of the tensor modes will tell you directly the value of H, and therefore will tell you directly the value of the potential, or better to say, if you like, you can identify the energy like the fourth power, sorry, the 1/4 power of the potential, and we will have a measurement of a direct measurement of the energy of that was a typical energy during inflation. If that is happening, of course, most probably we will have the first evidence of high energy physics beyond the standard model. Of course, it's an indirect one. We know already that there are reasons to believe that the standard model is not enough. We have dark matter, we have neutrino masses, and so on. We know that the baryon symmetry is there. But this will be something that will relate the measurement to the scale of inflation, and it's incredibly important. This is an important piece of information that we are lacking so far. Because the measurement of the power spectrum 10⁻⁵ does not allow to fix H. It only relates H to epsilon. Okay, so the relation is model dependent. But the measurement of tensors will really pin down the value of the energy scale of inflation. That is the reason why some time ago there was so much excitement in the community. You might remember that there was this claim that by the BICEP experiment that they publicized the measurement of this object here through the polarization, and the corresponding scale was about 10⁻�XVI GeV. And of course, people in the high energy community got very excited because 10⁻�XVI GeV is the grand unified theory energy scale, and everything was coming into the place. But of course, afterwards, this measurement was disproved, and so on and so forth. So, unfortunately, we are not there yet. Okay? Now, let me just talk about one more thing, and then I think I will stop. And if you are interested in other subjects, you can look at the notes. The other thing, since I understand that most of you are working not in cosmology, of course, but maybe in energy physics, something that you can read out from this expression here is the following. So let's rewrite this expression for R, which is the ratio of the two power spectra, and let's rewrite it in terms of this epsilon thing. Now, the epsilon, if you remember, was 4 pi g Newton divided by h square times phi dot square. Okay. Now, I want to rewrite this expression in terms of the number of e-folds. If you remember, n, or in this case delta n, was the integral in h in dt. Okay, so I can rewrite this. Well, let's use this infinitesimal form. Okay. So you see, when I express the derivative with respect to time, I write it in respect to the number of e-folds. I get that this guy goes like 4 pi g Newton is, let's say, 1/m Planck square. Again, I don't care about a factor of 2s and so on. And then I have delta phi divided by delta n square. Okay, so this tells me how much the phi field is moving in a delta n e-folds. You can take the delta n e-folds that are missing to the end of inflation, for instance, or any scale you like. Okay, so now you see from there that you can relate how much the field is moving. So you can say that delta phi goes like what? Goes like m Planck If I take the square root of it, of this expression, when I relate it to this, okay, you have factor of order unity here, I don't put them, and then I have delta n. And then I have the square root of r here. Okay, that comes from relating these two objects. So this simple relation tells you that if tensor modes are to be measured, we require that the power spectrum of tensor modes is large enough. In fact, typical numbers are of order of 10 to minus 1, 10 to minus 2. Okay, in fact, 10 to minus 1 is already ruled out, but in any case, numbers of this order of magnitude. So you see from here that I learn that the excursion of the field, in order to have an enough amount of tensor modes to be measured, has to be of order of n Planck. So this is a relation that you can find in single field mode of inflation, and is a generic one. The argument is the following. Having hope in measuring the future amount of tensor modes implies, within single field mode of inflation, that the infradome field, whatever it is, has to be traveling for distances which in units of n Planck is over a unity. Some people consider this a problem because they say that, of course, if I have a theory where the excursion is of order of n Planck or larger, any potential that you write down is not trustable, because I would expect a correction, non-renormalizable correction of order of delta phi over n Planck to some power p, where p is larger or than 1. Okay? And of course, if I have correction like this, and you don't know the coefficient in front, then some people say that, in fact, based on this argument, any trustable potential that you write down for inflation will suffer of these corrections, and therefore this will ruin your preferred inflationary model. And this is an argument to say that if everything goes right, then of course you should have fluctuations which are much more, excursion which are much more than Planck, and therefore tensor modes will not be measurable. So there is a lot of discussion about these kind of arguments in the literature. There are people that are okay with this argument. Some people are not okay. But this is a nice connection between something that you can measure and something that goes deep into the high energy physics models at high energy. Okay, so it's something that if tensor modes will be measured, it's an argument that will become very popular, I would say, in the high energy physics community. And I think it's the right time to stop. So I thank you all for your attention and questions and so on. And I'll stop here. Thank you. I don't know if you have any questions or curiosity. Yes.